Full Kirchhoff analysis. We've had the Kirchhoff voltage law. That's the one where you walk around in the circles and you say all the voltage ups and downs balance to zero. And then last time we played with Kirchhoff's current law, which has to do with junctions. The current in equals the current out. So now that we have both of these laws, I can start to show you at least how they get used together to do circuit analyses. So if you take a look at this first circuit here, you'll notice it has kind of like more branches to it than the other ones did. Let's identify the branches, in fact. So you see this 5 ohms right there? That counts as a branch. It counts as a branch because we've got a junction here, right? This is where wires are coming together and you need a little bit of solder perhaps to keep this together. And we have a junction here. So between the junctions, it's all the same branch. So that's one branch current. Notice that over here, this is all one branch. From here to here is all one branch. And actually from here to here is all one branch as well. So we've got 3 branches here, 3 branch currents. Now you'll notice that step 1 says draw arrows representing the current flows in each branch. Now before I do that, I need to call your attention to this thing over here because that's a new symbol. We haven't seen that before. We have seen this symbol before, right? Remember, that's a battery. That's a battery. So it's an 85 volt voltage source, you might say, is the official name. It's a voltage source. We have 85 volts of pressure, electrical pressure, right here. It's like a pump. It's trying to pump the electrons out the negative terminal with a pressure, electrical pressure of 85 volts. Okay, that's what that is. That we know what that is. These are resistors. We know what those are. But what the heck is this thing? Well, you got a nice clue here because it says 5 amps. This is a current source. So it's a little different from a voltage source. A voltage source forces 85 volts across its terminals. A current source is actually going to force 5 amps through it. So it's a little different. So batteries, you know what batteries are. What counts as a current source? I wonder if you have any idea of a practical example, a real-world example, something people can relate to. What would count as an actual current source? I could think of 2 things, and the first is cheating. You know those power supplies that you can put on your workbench? Well, you could set it to do volts, or you could set it to do amps. So you could use one of those, but that's cheating. But the other thing you do is solar panels. Very common example. Solar panels tend to be current sources, not voltage sources, but current sources. You get a stream of electrons, and the voltage is kind of unknown. What you know is what you know what the current is. So I'm not saying this is a solar cell, but we know it's 5 amps. And so I'm actually going to say 5 amps. Okay, 5 amps. Now that's flowing right here. I don't have to label it because it's already labeled. 5 amps is flowing right there, right? But notice what the implication is. This current has to be the same coming around the corner. This current has to be the same going through this resistor. That is 5 amps of current going right through that resistor. It's got to be. It's all the same branch. There's no junctions between here and here, so it's 5 amps. Now, when you get to this junction, however, things change, okay? So you can't just say, well, it's 5 amps there and, you know, it's going to be 5 amps here. No, it's not. No, it's not. If it is, it's a real heck of a coincidence, but it's probably not. Because this is a completely different branch. And so I'm going to say, okay, maybe I'll look over at this other power supply. It's an 85 volts. And remember, the way that these things want to work is they want to have current going out their negative terminal. So let's just assume it is. It's got, and how many amps is it? We don't know. So you have to label it with an X because that's what we mean when we don't know. We call it X. Now, if that's going to be X amps, it continues around the corner. This is all the same branch. And so here we've got X. And I'm not going to write amps every single time, but you know what it is. It's X is the current. X amps is the current going through that resistor. Now take a look at this junction here. Right now, the way I've got things drawn is I've got some flow coming in and I've got some more flow coming in. Well, you can't just have flow going in. Something's got to go out. And so my guess is that this is flowing up like this. Okay. Now I'm saying guess because I don't know for sure that over here that this is actually flowing down. How do I know? I suspect it could be, but for all I know, it goes this way. We don't know. But don't let that worry you. Just draw the current in a way that seems to make sense. Do your math. And if you happen to get a negative answer, that tells you, whoops, you drew it backwards. That's no big deal. Just the negative is part of your answer. And again, it indicates that you drew it backwards. So, getting back to this junction on the bottom here, junction A, if you will. I guess I won't put A because you might think it means amps. But that junction there, we got two flows going in. And remember how this works. I'm using Kirchhoff's current law right now. What goes in must go out. And coming into this junction is both the X and the 5. And going out is, I guess I could have called that a Y. But notice I can now erase the Y right away because I have just solved for Y. This is solving for Y in turn. It's X plus 5. This is X plus 5. X plus 5 represents the amps going through that resistor in the middle. And this is how I encourage you to label your currents. Label the X when you have to. You come across something, you really don't know it, you have to call it X. I knew what this was. It was a 5, so I didn't have to call this X or Y or Z or anything. This one, I guess I called it Y temporarily, but then because I was able to solve for Y with an X, in terms of X, I'm just going to label it this way instead. It's X plus 5. Let's get rid of some of this stuff here. So this shading, we don't need this much shading, do we? Yeah. By the way, you could sort of maybe get at this quicker. If you don't want to have to write in equals out every time, you can just by inspection. Say by inspection, these are combining. X and 5 combine. They must add up and go out. Just talking to yourself sometimes. You can figure out to label that X plus 5. Anyway, where are we on this? We drew the arrows representing the current flows, and without even announcing it, we just did step 2, labeling all the arrows using the current law. So the arrows are labeled. What's next? What's next is we're going to put the minus where your mouth is. I stated this differently last time we were putting minuses in. I said, look at where the current is. Do you remember this? I said, look at where the current is coming in. Since the current, the way we've drawn the current is coming in on this side, so the minus will go there. Plus goes on the other side. You only look at the way you've drawn the current. You don't look at anything else, just the way you've drawn the current. And the way I've drawn the current is that way, so the minus goes there. Looking only at the current, nothing else. I say, well, the flow's coming in the bottom here, so that's where the minus goes and that's where the plus goes. Here's a resistor. Looking only at the current through the resistor, you say, well, it's coming in the left side. And it's going out the right side. So that's how you do resistors. I say minus where your mouth is. If you think of, you have to blow through this resistor to get it to flow. You're blowing through the resistor. Well, your mouth is kind of over here. That's supposed to be a mouth. Your mouth, that doesn't look like much of a mouth, does it? Just imagine it was a mouth. So you'd have to kind of, maybe I'll draw it like teeth. Well, anyway. The part where you have the high pressure in your mouth to blow it. If you're trying to blow this through this way, this is where your mouth will be, blowing through the straw. This is put the minus where your mouth is. That's what that's saying. So if that's a catchier thing for you to remember, then just go ahead and do it that way. But the minus is where the current comes in. Sources, the minus where it wants to come out. Well, the battery, it wants to come out the negative terminal. That's where I'm putting the negative. And the reason I'm saying it that way is because how do you handle this current source? You say, well, the arrow is pointing this way, so it must want to, that's the way it wants to go. Put the minus there, put the plus there. Now, how many volts is it over here? I don't know. So I'm going to put a special script V. That stands for how many volts we've got here. This is the step B that I'm talking about, little b. Voltage across a current source is, I'm using a fancy V. I don't want to use a straight V because I might just think it means volts or something. It stands for the voltage, but it actually stands for a number that we don't know. It's a variable. We don't know what the volts is across that thing right now. If you wanted to, you could. I don't do this because it gets cluttered, but you could start saying things like, well, the voltage here is going to be 10x volts and so on. Remember, for a resistor, you multiply I times R, x times 10 or 10x. I don't like to do that because it gets way too cluttered. I'll just save that for when we're walking in circles. So that's kind of what the next step is walking in circles. I'm going to walk in circles. Now here's the cool thing. We're going to walk. You have to walk a loop. Make sure you walk a loop. Which loop? You got your choice. You've got loops everywhere. Here's a loop. If I just walk around this loop, that would work. That's a loop. You start and you end at the same spot. That's a loop. I could go like this. That's a loop. That works too. Or I could go like this, walk around this side. Okay, so I got like 3 possibilities I can play with here. I got 3 loops I can play with. Now the loop I'm going to walk through is the first one. Do the right side. Do the right loop first. And the reason I'm doing the right loop first is because I try to avoid the current source at first. Why am I avoiding the current source? I'm avoiding the current source because I don't know what the volts is. It's like an extra unknown. I don't want to deal with an extra unknown if I don't have to. I would rather just kind of maybe start here. Here's where I'll put Ant-Man. And I'll have him walk around maybe this way to the right, clockwise. Okay, here he goes. Ant-Man's walking. He's walking around and he has to write down all of his changes in voltage. So notice that when he comes into this battery here, he sees a plus on the way in. So I'll put a plus here, and you get the volts, and it says it's 85 volts. They don't call it the voltage law for nothing. Kirchhoff voltage law, you're balancing volts up and down. So coming through the battery, I see a plus on the way in. So on the way in the door, grab the sign, it's a plus. It's 85 volts. Then you come around, here comes the ant. He comes around this way. Now he sees a minus on the way in, which means the next thing he's going to encounter is a drop in voltage. And how much is it? Well, you got to remember, I need volts, and that's not volts, and that's not volts. But it is volts if I multiply them together, right? That's how resistors work. The voltage is equal to the ohm times the current. So my volts there is 10. Pop out the other side, take a hard right. That's a right? Yeah, take a hard right, come up here. Oh, I see a minus on the way into my next resistor, so it's going to be a subtraction. I'm going to see the volts go down again. And again, I need volts. That's not volts, that's not volts, but if I multiply them together, that's volts. So I'm multiplying a 5 times an x plus 5. And that has to go in parentheses like that. Good thing we learned how to distribute before, huh? Yeah. So I have to multiply the 5 times the x plus 5. Come around, come around. I get back to where I started. As soon as you're back to where you started, you finish your equation by saying equals 0. So there, we walked a little loop. Maybe I can do this. We walked a little loop. Starting here, we went around, we wrote our ups and downs for voltage. And we got that nice equation, which we can solve. Distribute first, so that's an 85 minus a 10x. Remember how distributing works. You have to take this minus with you. Minus 5x. And then a minus 5 times a 5 makes a minus 25. That equals 0. So this is all on the same side. It's all on the left side, so I can put like terms together. If I use my numbers first, I got an 85, take away 25 is a 60. And if I do my x terms next, I got a minus 10x minus 5x more is a minus 15x. So 60 minus 15x equals 0. I can add 15x to both sides. Remember, keep your sides separate. And that'll give me a 60 over here and a 15x over here. And the last thing you do is you divide both sides. And remember, you look at the x. Here's the x. So what I have to do is I have to put a 15 on the bottom of both sides. Cancel off the 15. I've got x equals 60 divided by 15 is 4. And we just solved for our first current. Remember, x's and y's, they always stand for current. So I just solved for current. Now, where is that current? That current is right here. It's going through the 10 ohm resistor. So let me do that. Through the 10 ohm resistor, I've got a current of 4 amps. See, I can start writing some stuff down here. By the way, well, here's x again. So through the battery, through the 85 volt source, I've got 4 amps. Cool. So what else have I got here? Well, through this 5 ohm resistor up here, the amps is actually, it's the way I've labeled it here. The amps is x plus 5. So it's x plus 5, and so maybe I'll just kind of put that there as a reminder. I labeled that current x plus 5, and since x is 4, I got 4 plus 5, which is 9. Through the 2 ohm resistor, well, I guess we knew right away it was 5 amps, and through the 5 amp source, it has to be 5 amps because it's a 5 amp source. So there, we got all our currents. Now we can start solving for voltages. Here's a nice way to solve for these voltages. You'll use green now. Remember, for a resistor, you multiply the resistance times the current. So 10 times 4, this is 40 volts right there. 5 times 9, this is 45 volts right there. 2 times 5, we got 10 volts across that one. I could come over here, see it says it's an 85 volt source, that means it's 85 volts. Okay, so be careful, don't multiply 85 times 4. Nah, don't be that quick or whatever, don't be too fast. It's an 85 volt source, that's why it's 85 volts right there. That's 85 volts, that's 85. That's 85 volts. Okay. This is a current source. It's 5 amps, it's 5 amps. Okay. What's the volts though? Well, remember we used this script V over here because he said, I don't know what it is. Now we know it's 5 amps, but we don't know what the volts is, and we don't know the resistance either. So we can't even multiply 5 times the resistance. We just don't know what it is. So how are we going to get it? We have to walk another circle. Let's do left loop. Walk another circle. Every time you need an equation, you walk another circle. So instead of Ant Man, let's have, what was that woman's name? I can't remember. So I'm just going to call this Ant Woman. There was another one. What the heck was her name? She had her own costume and everything. No, anyway, just call it Ant Woman. And have her walk around, and it doesn't matter if she walks to the right or walks to the left. It totally doesn't matter. Maybe I'll just walk the same way. I'll go to the right here. I'll come down the middle, and notice I'm seeing this plus on the way in. And then I want my volts. Well, notice that for the 5 ohm resistor, I just solved for the volts. So I don't have to write 5 times x plus 5 because I already know it's 45 volts right there. Ant Woman comes out, takes a turn. She's coming over here. She sees a plus on the way in, and now she needs the voltage for the 2 ohm resistor. She needs that voltage. Well, the 2 ohm resistor has 10 volts. We already solved for that. Cool. So we got the 45 volts there too. Okay, Ant Woman comes out this way, and now she sees a minus coming into this thing, which has the special script V. We don't know what it is, volts. And then we come out, we're back where we started, so it equals to 0. And this equation, real quick like, is going to solve to tell you that the volts over there is 55 volts. And so now we can finish our table. 55 volts across that 5 amp source. Good news is all of my current answers came out nice and positive, which means my arrows are correct. I didn't get any arrows wrong. That's good. Of course, if I did get an arrow wrong, I wouldn't care. I would just put the negative in my answer and keep moving. So, okay, that's one full example of a Kirchhoff analysis. Basically a 4-step plan, 5 if you count actually solving and filling in the table. But draw your arrows, label your arrows. Put the minus pluses in and walk around. Walk around. You might have to walk around more than once. Here's a fancy looking circuit. Let's just do this one too. And it looks like it must be weird, right? But it's not. It's the same kind of stuff going on. Where's the junctions? That's your first question. Well, there's obviously a junction right there. There's like a T junction right there, and there's a T junction right here. And it turns out those are really the only junctions separating branches, because from here to here, it's all the same tube. It's all the same hose. It's all the same pipe. That's one branch. Starting here, this is all one branch, right? From junction to junction. That's all the same current from there to there. And this has to be all the same current from here to here. Current can't change until you get to a junction. So we've got 3 branch currents. We should label them. Actually, this one's already labeled for us. It's 5 amps right there. What's going on over here? I don't know. Looks like I got a battery trying to push up, so I'm going to guess that it's pushing up. And if that's X amps, then that's also X amps because it's all the same junction. Okay. So what's going on over here? I'm going to come up to this junction. So notice I've got X coming in, and this is 5 that's going out. And then here I can say that this is going up, or I can say that it's going down. It doesn't matter, because again, if I get it wrong, I'll just get a negative answer. But let me draw it going up, and I'll call that Y for now, and that's a 5. So at this junction, in goes out. What goes in is X, what goes out is a Y and a 5 combined. And that tells me that I can actually, instead of using a Y, I can solve for Y right now. It's X minus 5. And so that's how I'm going to label this. I'm going to label this as X minus 5. So this current comes around this way, comes around this way, and coming through here, the amps is X minus 5. And then coming through here, the amps is X minus 5. So I've got 3 branch currents. This is all X through this loop. This is all 5 amps in this loop. And I've drawn it this way. This will be X minus 5 in this loop. Those are my 3 branch currents. That was drawing arrows. That was labeling arrows. 2 steps down, 2 to go. Resistors, put your minus where your mouth is. Yeah. So here's a resistor. I'd have to put my mouth on this end if I wanted to blow through that way. I'd have to put my mouth on this end if I wanted to blow through that way. I'd have to put my mouth on this end if I wanted to blow through that way. I think that's quicker to think about, actually. Where the current enters, put a minus. Yeah, where you put your mouth, put a minus. Minus where your mouth is. Anyway, those are my minuses there. Now the battery is stamped with the plus, so we can believe that, and then this has to be the minus. And then you might remember, well, it says it right here. For any kind of source, the minus where it sort of like wants to come out. So this is a current source here, and it wants to pump it this way, which means that's my minus. Notice sources are the opposite of resistors. Yes, they are. Because the current's coming in this way, but that's not where the plus is. I mean, that's not where the minus is. If this were a resistor, if the current's coming in, you put the minus there. But here the current's coming in, and that's where the plus is. So these things are a little bit different. The sources are different. So, okay. So I guess we did that. Got all our minus pluses set up. So it's time to start walking around. Again, we got 3 choices of loop here. 3 choices? Yeah, I think 3 choices, because you could walk around here, the inside loop. That's 1. But notice what else you could do. You could kind of walk around this way, around the whole outside. That would be like 2 loops. Or you could walk around here and cut through the inside like this. So that's 3 loops. Yeah, there's actually 3 loops possible that you could walk around. So I try not to walk through this yet. Save that for last. Save the current source for last. So where am I going to walk? I'm going to walk around the outside. Just so I don't want to go through that right now. So I'm going to walk around the outside. Where should I start? Doesn't really matter. Maybe I'll have Ant-Man start here this time. And we might as well have him follow the current around. Again, it doesn't really matter as long as he walks around in a circle and gets back to where he started. That's what matters. So he's here. He's walking. He sees a plus on the way in to a 20-volt battery. And since it's the voltage law, we want volts. And since it's 20 volts, we put a 20 there. Ant-Man pops out the other side. He's coming into the next circuit element. He sees a minus on the way in. Put the minus there. I need the volts. Again, resistors. That's not volts. That's not volts. But if you multiply them, it's volts. So it's a minus 10x volts there. Ant-Man comes out. Well, he wants to take a corner and come around the outside, so he takes the corner. He's going around the outside, going around the outside. Now he sees a minus on the way into this one. And again, it's a resistor. You have to multiply this times this. So that's 4 parentheses, x minus 5. Keeps walking, keeps walking, keeps walking, keeps walking. Comes over here, sees a minus on the way in, and has to multiply 2 times an x minus 5. Okay. Comes out, comes out, comes out, comes out. Take our target back where we started. Finish the equation by saying equals 0. That's the voltage law. All the changes of voltage have to sum to 0. Now we want to solve this thing. 20 minus 10x stays the way it is. This is called distributing. Take a minus 4 times x. Take a minus 4 times a minus 5 is a positive 20. Over here, minus 2 times x is minus 2x. Minus 2 times minus 5 is plus 10. Make sure you're handling this negative times negative properly. And that all equals 0. All my terms are on the left side, so I can start combining like terms together. If I look at x terms, I got this, this, and this. All of those are x terms. They can all just be added together. Notice all 3 of them are negative, so it's going to be a big negative that I get here. 10, 4, and 2 makes a negative 16x. Then I got the numbers. I got a 20. Add 20 is 40. Add 10 is 50. Wow. So I got a negative 16x plus 50 equals a 0. And I think what I'll do this time is I'll subtract the 50 on both sides like this. And then I should divide both sides by the negative 16 like this. And let's get a decimal out of this thing. 50 divided by 16 is, I'm getting like 3.125. And this would be amps. And that's part of our answer. X is 3.125 amps. Question, where do we put it in the table here? Well, you refer to your circuit diagram again, and you say, well, here's where X is. It's going through the 20 volts. Well, this table's not labeled right, is it? Make this say, that says 10 ohm resistor, but we also have a 4 ohm resistor and a 2 ohm resistor. Okay. We have a 5 amp current source, but that's not 85. That's a 20 volt voltage source. How about that? Fix that up, please. And now we'll start cranking. So we have X going through the 20 volts. X was 3.125. We got 3.125 amps going through the 20 volt. That same current X is going through the 10 ohm. So through the 10 ohm, 3.125 amps. Cool. Through the 4 ohm over here, we have X take away 5. So I'm supposed to go X take away 5. Now notice if you go 3.125 and you subtract 5, you get a negative 1.875. So it looks like the current's not going that way, it's going the other way. Oh well. I'm just going to leave it as a negative 1.875. The 2 ohm resistor has the same current as the 4 ohm resistor, so this is also negative 1.875 amps. And to finish up our currents, it's a 5 amp source. That's what it does. It forces 5 amps. That's what a source will do. If it's a 5 amp source, it sets up 5 amps. The voltage, who knows what the voltage is going to be, but it's going to set up 5 amps. If it's a 20 volt source, that's what it's going to do. It's going to set up 20 volts. Who knows what the current's going to be, but it's going to be 20 volts. Okay, that's what that does. So what are we left doing here? Well, we're left trying to solve for some voltages, right? So let me start solving for some voltages. So remember, for resistors, voltage is equal to current times resistance. So for this resistor, I got this current times this resistance. 10 times, it's going to give me a 31.25 volts. Here I'd have 4 times a negative 1.875, which is, oh, what the heck is that? 4 times a 1.785 is a negative, so, what? Let me try that again. 4 times 1.875. There we go, that's better. So this is a negative 7.5 volts right there. 2 times that is going to be negative, what, like 3.75, I want to say? Sure. And then the only thing we haven't solved for is what's the voltage here. Remember, for the current source, it's a special deal. The current source is forcing 5 amps, and the voltage is going to float so that everything works out. So we have to figure out what's the voltage by actually walking through it. We need to walk another circle. So let's walk the inner loop. We'll have Ant Woman start, doesn't matter. Maybe well, let's do Ant Man again actually, but he's going to walk around the inner loop. So he starts here, he's going this way. He sees a plus on the way in, and it's 20 volts. Woo-hoo. Then he comes out here, he sees a minus on the way in. And have we solved for the volts here yet? That's the 10 ohm resistor. That's 31.25 volts. We've solved for it. He comes around, comes around, comes around. He sees a plus on the way in, and this is where we put that special script V, and then he's back to where he started, equals 0. So 20 take away that is a negative 11.25. Add the V equals 0. If you subtract, well, add this on both sides, I suppose, would make be a good idea. Then you end up with V is equal to 11.25 volts. Right there. So always save that for last, walking through the current source. Save that for last. I'm trying to take a quick look at whether I'm getting answers that I used to get. And it looks like I'm getting answers that I used to get. That's good. That's a good sign. Okay, so it's kind of a, usually people say, wow, that's a long process. And it kind of is. I guess a lot of times in math class, you're used to just do 1 step and you're done, or maybe 2 steps and you're done. This is like, well, I've got it as 4 steps, but really it's probably like 10 steps, right? But each step, if you know what each step is, then you can move to the next step, do that one. Move to the next step, do that one. This is good. It builds up your, what was I going to say? Tolerance? That's not what I mean. Endurance. There's a good word. Builds up your math endurance. Can